this lecture, we're going to be looking at the complexities of the scattering area coefficient K from the last lecture. And what we want to do is we want to plot the scattering area coefficient as a function of the size parameter, and the size parameter alpha is going to be defined as 2 pi the radius over the wavelength. And so this is really looking at the relative size of the scattering object relative to the wavelength of the radiation that is going to be hitting that object. And when the size parameter is very small, the scattering area coefficient is likewise very small. And then there's a middle size range for the size parameter where we have this oscillatory behavior in the scattering area coefficient, and then it damps all the way down to a factor where when you have very large size parameters, so very large particles relative to the wavelength of light, the scattering area coefficient is essentially constant at a value of 2. And so we have these 3 different behavior regions for scattering area coefficient. We have the scattering area coefficient we basically define this into 3 groups. When the size parameter is much, much less than 1, we refer to that as the Rayleigh scattering regime. When the size parameter is between about 0.1 and 50, we refer to that as the Mie scattering regime. And when the size parameter is greater than 50, we refer to that as geometric optics. And so if we look at each one of those individually, so the Rayleigh scattering, the size parameter is very, very small, which means that we have very, very small radius relative to the wavelength that's coming in. And this is going to be appropriate for all gases in the atmosphere and extremely small particles that are usually associated with combustion, very near the source. And in the Rayleigh regime, the scattering area coefficient is proportional to the size parameter to the 4th power. So if you think about how a function would look, if it were proportional to the size parameter squared, it would look like this. If it were proportional to the size parameter cubed, it would be this. But in the Rayleigh scattering regime, it's actually the size parameter to the 4th power. So it's not really going to look like that. It's just going to be a very rapid increase in the scattering area coefficient with the size parameter. And what that means, it means that shorter wavelengths are going to be scattered much more efficiently than our longer wavelengths. In the Mie scattering regime, with the size parameter between 0.1 and 50, this is going to be the appropriate scattering regime for most particulate matter in the atmosphere, with the exception of the combustion particles and haze droplets, which are the non-activated cloud droplets. And for Mie scattering, that K value oscillates with the size parameter, and it also depends on the index of refraction of the particles as well. And it's very complicated, requiring numerical solutions in order to be able to get that, or lookup tables. And by contrast, for geometric optics, when the size parameter is very large, this is appropriate for cloud and rain droplets and ice crystals. And that one's very simple because the scattering area coefficient is just equal to a constant value of 2.